What I want to talk about today is something I'm fiddling with for quite a while now. And it is unfortunately still less specific than I would want it to be. But nevertheless, I think that it is a crucial issue for understanding the status of fundamental physics today. So I want to start with the main claim of this talk, and then we will see to what extent I can make sense of that claim. The talk is about final theory claims, and final theory claims have been fairly popular and were frequently discussed in the context of string theory in the 1990s. We remember Meinberg's famous book, for example, or Witten has written about it. There were several important and quite conspicuous contributions discussing final theory claims. However, what happened in the early 2000s until today was that optimism regarding the further development and completion of string theory in the foreseeable futures decreased. And that has led to also to a decrease of discussions on final theory claims. They are clearly much less popular today than they used to be 20 years ago, let's say. And what I want to claim is that actually this is an important time, a good time to discuss finality. It is particularly important to discuss finality at this point because finality may be a main reason why the completion of string theory is so elusive. And this is not just about string theory, but it is also about the issue of developing a theory of quantum gravity in a broader sense. Now, the kind of finality that will emerge here is quite different, however, from the traditional view. And part of what I try to do is try to understand how this concept would differ and how a more meaningful concept of finality in the current situation could be constructed. Now, this is about string theory in particular and about quantum gravity more generally. And how to reconcile quantum field theory, theory of particle interactions with general relativity clearly is a core challenge, maybe the core challenge for fundamental physics today. And string theory is the leading contender in this, the leading contender for a full solution there. But there is a wide spectrum of approaches that addresses aspects of that problem. And all those approaches, in a sense, are in the same boat. So what I will be saying in the context of string theory probably has wider relevance. Let's start with a conspicuous problem of string theory today, what I want to call string theory's chronicle, incompleteness. String theory has been proposed first in the late 1960s and then in 1974 proposed as a theory of all interactions. And then from the 80s onwards, it had quite remarkable successes. And in particular, after the discoveries of the web of dualities in 95 and ADS CFT correspondence in 1998, string theory was taken to have a decent prospect of finding, let's say, at least a substantially more complete formulation in what was then the foreseeable future. Now, what has happened in the last 20 years or so is that those hopes have been dampened. So there have been significant improvements in the understanding of some aspects of the theory since then, but it appears as far from completion as ever, one may say. And a long list of fundamental issues related to a theory are still unsolved. So there is this question of enigmatic M theory. What is M theory? There is still, related to this, maybe there is still the fundamental question, what is the fundamental mechanism that selects a string theory ground state? There are those duality relations, and there is the question what exactly the status of those dualities is. So, for example, is ADS-CFT a precise duality between two perspectives of equal status, or is there some kind of hierarchy between those perspectives? There is the question whether ADS-CFT is a specific case of a general gauge gravity duality that might also be formulated. There are still lots of open questions with respect to a stringy understanding of black holes, and so on and so on. So after 50 years of work on the theory, the prospects for a completion of string theory in the foreseeable future seems maybe even less clear than it was, let's say, 20 or even 30 years ago. And this open status of string theory has led some exponents of the theory towards not calling it a theory specifically. So David Gross, for example, calls string theory a framework like quantum mechanics or quantum field theory, which is a framework within which specific theories can then be built. And the understanding, to some extent, is that the ground states of the theory would then, or specifying ground states of the theory then would amount to specifying a theory. And while this accounts for the theory's conceptual incompleteness, and also for the high flexibility with regard to choosing ground states, it arguably does not quite represent the rigidity of string theory at a fundamental level, which is also a conspicuous characteristic of that theory that will play an important role later on in our discussion. So many string theorists, maybe most string theorists, would view string theory as something like a well-defined theory in progress. So, for example, Maldacena, in a very recent paper, characterizes string theory this way. He says string theory is a modification of Einstein gravity that leads to a well-defined perturbative expansion and also some non-perturbative results. For this reason, it is believed to define a full theory of quantum gravity. So, meaning that we do know a lot of stuff about that theory, and that stuff we know is sufficient for identifying a full theory of gravity that we don't yet have. We are not yet able to fully spell out that theory, but what we know about the theory, the posits we have introduced in our understanding of that posit, is sufficient for understanding that we are aiming at a specific theory, that we are working on a specific theory to be fully developed. So there is this understanding that there is a theory among the majority of string theorists, but there is no prospect of completing the theory in the foreseeable future for solving this long list of fundamental problems the theory poses. And it's important to point out that this is not a problem of one theory. It seems to be a problem of the question posed, of the question, how can we develop a full theory of quantum gravity? And the difficulties to complete a theory also pop up in other contexts where quantum gravity is dealt with, such as loop quantum gravity, spin foam, group field theory, or others. So there seems to be something about quantum gravity that makes it conceptually particularly tricky to develop into a full theory. So that is the first point. That's the issue of chronicle incompleteness. And on the other hand, there are a number of arguments that suggest that string theory, if viable, could be a final theory. And I want to highlight three arguments, or three groups of arguments maybe, that point in that direction. The first argument is a very general one. Not everyone agrees how strong of an argument that can be, but string theory is a universal, unified theory that covers all fundamental phenomena, physical phenomena that we are aware of. So it describes all known interactions and particles, and it aims at giving a unified account of all interactions. Now, if one takes theory dynamics to aim at increased universality, then this kind of full universality is a natural endpoint. It is the point where one can say, okay, maybe we have arrived at a final theory here, a final theory of fundamental physics. Equally, if unification is viewed as an aim of physics, then full unification of all fundamental physical phenomena is a natural endpoint along the same lines of reasoning. So already these considerations may suggest that actually taking the overall process of physical evolution as a unificatory process towards higher universality, then this is the point where we might suspect that the last step has been taken. In addition, there is the point that string theory only works as a universal theory. So it offers no options to connect it or embed it in another theory. And that's of course related to the first 2 points, but it's not the same point. It goes beyond that. It's not a trivial step to remark that is what the theory is like. So from the inside, from looking at the situation from the string theory perspective, let's say, the theory suggests that there cannot be more in this world than what it allows for. Now, this from the inside perspective, of course, is an issue, and we will come back to that a little bit later on. But still, it is an argument. It amounts to a genuine string theoretical argument in favor of finality. Then the second reason to suspect finality in this context is the famous minimal length scale of string theory that was, for example, discussed in detail by Witten in a paper in a philosophy of physics volume. The point is that in string theory, we have dualities that relate various theories or formulations of the theory to each other. And those those theories or realization of the theory are empirically equivalent based on the duality claim. One of those dualities is T-duality that leads from one theory to another theory with inverted length scales. So, for example, you can have a type 2A string theory, so a certain type of string theory where you have closed strings with a momentum n around in a compact dimension of radius r, and then T-duality will lead you to a type 2b theory where this phenomenon reappears as a string wrapped around a radius, a compact radius, a compact dimension of radius 1 over r, and the theory has a binding number. Now this relates a length scale to an inverted length scale. And this implies all in general that T-duality establishes a minimal length scale by offering the possibility to translate all distances smaller than L into distances L square over D. So where L would be the characteristic, D would be the characteristic length of the theory, the string length. This means that information on smaller distance scales is fully redundant, and that means that if string theory is valid at its characteristic scale, so up to this scale D, no new theory can kick in at a higher energy scale, because the validity of the theory up to D, the precise validity, would already establish that this includes all redundant information that would be expressed in length, terms of length lower than that distance scale. Therefore, once again, from an internal perspective, from the perspective of string theory itself, the theory looks final. It tells us if it is valid up to its own characteristic scale, then there is no sense of talking about other scales, about higher energy scales, lower distance scales. Now, of course, there is a basic worry in this, and that is the internal perspective, the theory internal perspective. Clearly, the described claim relies on the framework provided by the given theory itself. And therefore, it seems to be begging the question, because a successor theory to string theory may not actually contain T-duality. So it may be that string theory actually is not exactly viable at its own characteristic scale. It's just some kind of approximation. And that would mean that there would be a more precise theory that maybe does not contain T-duality and therefore can deviate from string theory at high energy scales. So in that case, this more fundamental, more accurate theory would overpower, so to say, the final theory claim of string theory. Therefore, it's clear, first, it's very clear that the argument previously discussed is not conclusive. It cannot be a conclusive argument. And it's also clear that the final theory claim of that kind cannot stand on its own. And the question is, does it mean that it is meaningless? And I don't have the time to discuss this in detail. I tried to do so some time ago in the context of scientific underdetermination. And in that framework, I argue that it is not meaningless. It is nevertheless a relevant argument, even though it cannot be a conclusive argument. And the reason is that these kinds of arguments can be supported by arguments of local limitations to scientific underdetermination. And so arguments regarding the spectrum of possible alternatives, and only support by such arguments can turn such a final theory claim into a relevant argument. And this is less of a serious condition, I would claim, than one might naively think, because I would claim that if you look very carefully, any argument that pertains to the stability of any theory and the predictive reliability of any theory must depend on arguments of local limitations to scientific underdetermination. So I would claim that in this sense, clearly final theory claims are more tricky than other arguments of reliability, but what makes them reasonable arguments is not in principle of a different nature than support of other elements of other arguments of reliability of scientific theories. Now that would be the second argument. And the third argument actually is the argument that will play the main role in this talk, and that is the point that string theory has no fundamental free parameters. At a fundamental level, string theory is a rigid theory. There are many ground states of the theory, the string landscape, but there are no fundamental dimensionless free parameters. And this is a highly unusual characteristic of a physical theory. Normally, physical theories do have dimensionless parameters, either free parameters, either dimensionless free parameters that play out within the theory, or in rare cases where that's not the case, if there are no universal theories, they do have some parameters that can be compared to parameters in the outside, that characterize the outside world, so to say, that measures the phenomena described by that theory. Now, in the case of string theory, none of this happens. There are no dimensionless parameters, and it is a universal theory. So there is no way to adapt the theory at all at the fundamental level to phenomenology. And of course, as we know, this is countered by the fact that there is this huge set of ground states. But those are two different things: the fundamental level and the spectrum of ground states of the theory. Now, this lack of free parameters provides another piece of support for finality, I would claim. And there are two levels at which one can identify such an argument. The first one is similar to the finality arguments I've given before in point one. If one thinks that free parameters is something that needs to be explained by scientific theories, and whenever I have a parameter value that is fixed and that it cannot be explained at the basis of the given theory, I want to look for a new theory that can explain it, then a theory that does not have any free parameters is a natural endpoint. Once I have reached that, then I can say, okay, this task is fulfilled, this is done. So therefore, a theory of that characteristic is a natural final theory candidate in this sense. The second point is that the second argument can be understood by thinking about the situation that we have found such a theory without free parameters that is viable, let's say, at some level. Now, one might say, in such a case, it's not plausible to have a succession of theories without free parameters, let's say an infinite succession, or even the next theory, because theories without free parameters are so rare. So while it is fairly plausible, one might say, to find a next level of theorizing where I have parameters I can play with, it is much more difficult to find a different new theory that exactly fits the characteristic of having no free parameters that is represented by the theory at hand. It is a very different situation, and assuming that the succession of theories is plausible in the context of free parameters does not imply that it is also plausible in the absence of free parameters. Second, one might argue that if I have a theory without free parameters, it is not plausible to move back to a theory that has some, because the fundamental theory then would not be able to explain the effective one. The fundamental theory, where I can fix a free parameter, would not be able to explain why the effective theory is exactly the way it is, why the effective theory selects exactly one value of that more fundamental theory. And that would go counter to our understanding of the way in which fundamental theory and effective theory are related to each other. So those is a set of reasons that in conjunction may be taken to suggest that having no free parameters and being a final theory may be related, or a theory that has no free parameters may look like a plausible candidate of a final theory. So now I have those two observations. On the one hand, there are some reasons to think that the theory may be final. On the other hand, I have this peculiar situation that the theory is chronically incomplete. Now the question is, and those two characteristics arise in the context of the same theory. And the question is, does this fit together? How does this work together? And there is a widespread view, actually, that those two characteristics just don't. They push in different directions, seemingly. And one might raise some issues that suggest exactly that. For example, one might say, if you don't even know what the theory is, how can you even start speaking of making a final theory claim? Before making a final theory claim, you better know what you mean by the theory. You might also point out that having a final theory making a final theory claim, let's say, should rely on having high credence in that theory. Otherwise, the claim doesn't seem plausible at all. And one might also have the strategic comment that it would actually be highly counterproductive to make final theory claims at such a stage, because if we suggest that we have arrived at a final theory, that means that we should stop looking for new fundamental ideas. And if the theory is not even correct, then it would be just strategically misplaced to make such a claim. And those views are reflected in the recent history, ups and downs, of the notion of finality among string theorists themselves. As mentioned in the beginning, in the 90s, final theory claims were really quite popular. And that was a time when hopes were high that string theory would soon approach the status of a largely understood theory. They have fallen out of favor, however, in recent years after string theorists had become less optimistic. So it is very plausible to suspect that arguments of the kind represented at the top of that page play a role here. And these considerations are based on what I would call the traditional view on finality. And this traditional view on finality represents the understanding of, in particular, Newtonian physics, let's say in the 18th and much of the 19th century, where Newtonian physics was considered to be final. And it also applies to Maxwell's electrodynamics, the understanding quite some physicists had of Maxwell's electrodynamics in the later parts of the 19th century, where Maxwell's theory was also considered to be probably final in this sense. And so this understanding assumes that the final theory is the last substantially new claim on a subject matter Now, there may, of course, be improvements. There may be more elegant formulations in the context of Newtonian physics. That has happened, of course, as we know, more effective ways to calculate the theory's precise implications maybe, but there should not be, one shouldn't expect genuinely new insights that improve the theory's predictive reach, because the theory is what it is, simply. On that basis, the understanding is that finality claims can only be established based on a consistent and long-lasting predictive success of that theory. So one would, of course, only make a final theory claim if the theory looks nice, it does everything one wants it to do. But in addition, one needs to wait for quite some time to see whether the theory is so successful that at some stage one may say, okay, probably that's it, we have found it. And on that basis then, of course, once a theory has been acknowledged as final, it is plausible to say it doesn't make that much sense at this stage to look for new theories in that field. So in the early 19th century, it would not have been considered awfully advisable to look for alternative theories of gravity to Newtonian physics. So this is the traditional understanding of finality that was applied to Newtonian and Maxwell physics. And it is also the concept of finality that was taken to have been eternally discredited by the downfall of Newtonian physics in the early decades of the 20th century. So what happened then was that this meta-inductive argument saying the theory has been so successful for such a long time, therefore we think it is final, this argument just has failed. And then the question was, if it failed even in the case of Newtonian physics that was so successful for such a long time, how could we ever again believe the final theory claim? Now, the point is that the final theory claims of string theory, as discussed before, are not at all of that kind. They are not at all, obviously, meta-inductively based on consistent success, consistent predictive success, because there hasn't been predictive success of string theory. String theory has not been empirically confirmed at all. So the way the final theory claims in this case is either on one hand contextual, such as in the case of argument that string theory covers all fundamental physics, or conceptual, so based on internal conceptual characteristics of the theory itself, such as that it has a minimal length scale, no free parameters, that it's not extendable. Therefore, the traditional implications of finality don't apply either, quite clearly. The final theory claim in this case does not depend on conclusive or strong epistemic commitment. It is rather of the type, if the theory is viable, then maybe it is final. The final theory in this case, if it is incomplete, and it is highly incomplete in the given case, may still have fundamental shifts in store, fundamental shifts in understanding and perspective. And those fundamental shifts may be necessary to achieve any predictive power of the theory in that particular case. So in both senses, this final theory claim is far less, let's say, far less powerful with respect to establishing the status of the theory than the traditional perspective would suggest. What is essential, however, is the understanding that the posits that define the theory at this point are capable of uniquely determining the full theory. So something of the kind Malacena seems to indicate in his quote is necessary. If that's not at all clear, then a final theory claim does not make that much sense, because we don't even know what theory we are talking about when we just talk about the posits we're working with at this point. So it's clear that the final theory claim only makes sense if one considers that to be sufficiently well established. So that would be a very different perspective on finality. And I would want to characterize this, or to offer three pictures that characterize those three options we have. So first, the first picture characterizes a canonical view of theory succession, where there is no finality claim around and no expectation of finality ever, let's say. So the idea is that this blue arrow, the time until the end of science, is infinite. And what we have is a sequence of theories, the red arrows characterizing the construction time for a theory, and then the yellow arrows or orange arrows characterizing the lifetime of that theory until, let's say, it hits an anomaly, sufficiently serious anomaly that requires a new theory that supersedes the previous one. And that, the understanding is that will go on forever. I have finite construction times for each of the theories, and I have finite lifetimes for each theories. And there is an infinite sequence, which makes the time until the end of science infinite. Then there is the traditional final theory view, where at some stage this just stops, where we end up with a theory that after a while, after having established that it is extremely good and it is consistently predictably successful within its intended domain, let's say, or in that case, I would say at some stage, okay, probably that's a final theory. So that would be the understanding of Newtonian gravity in, let's say, the 19th century. In this case, the time until the end of science meaning end of fundamental theory building in this particular context, on this particular subject matter, the time until the end of science there is finite. It has ended when we have fully developed the theory. From that time onwards, of course, physics will go on, physics will look at more specific questions, but the fundamental theory is there and it's there to stay. No additional fundamental work to be done. And then we have the view that may be suggested by string theory today, and that would be the view that at some stage we end up with a theory that is not should not be expected to be superseded, but we also have no expected time horizon for the completion of the theory. So of course that one may point at a subtlety here that probably these, even though we just have one time horizon here, the status of those two claims may be different. So the final theory claim would be a stronger finality claim than the claim on construction time for the theory. The infinity claim for construction time of the theory is not literally an infinity claim. It just amounts to saying, I don't know whether any of the next generation will live to see that. I don't know either whether it happens at all, but I would not make a very strong bet on infinity there. I just want to say the expectation that there is a finite lifetime for theory development here is very weak, or say is not established, let's say. So in that case, what we find is that the time until the end of science, once again, is infinite, because both other arrows are infinite as well. The lifetime of the theory is infinite, and the construction time for this theory is infinite in this weak sense as well. So that would be the idea, and that would also amount to saying that there is a finite space of phenomena that can be specified, let's say, finite in a conceptual sense. Now, so as has been said, this does not mean that there is an absolute commitment to the validity of the theory. It just means if that's the theory that is viable at some stage, then that would be the most plausible framework to understand the situation. It might also, of course, lead to suggestions that the fact that the overall context is the way it is does strengthen the claim of finality due to the current situation we're facing. So there may then, in the end, be the idea that chronicle incompleteness and finiteness are somewhat related. So the fact that we observe chronicle incompleteness may support a finality claim if one wants to establish that there may be some connection between the two. So the question is there some way in which one might understand that finality causes or favors chronicle incompleteness? And what I want to do in the rest of the talk is to suggest that there is something of that kind. The idea would be that one of the three arguments I have presented, the argument of free parameters, is very relevant for the issue of chronicle incompleteness, and that's the issue of free parameters. Yes. So free parameters play two different roles. On the one hand, empirically, they allow to connect a theory to data. So I can choose the parameter in a way to link it, to make it empirically adequate in face of data. Conceptually, on the other hand, free parameters control the move towards and away from our intuitions. And those two roles are not unconnected, because our observation interfaces are classical. So in other words, we know that our world is of a kind that allows for classical descriptions of our part of a measuring device. So the normal case, the normal understanding of how intuition and heuristic works in a theory would be that we live close to a classical limit, and that our intuitions are shaped by that, while other parts of the universe are far from any classical limits. And more advanced fundamental theories then have the goal to reach out towards those parts of the universe. And now moving from intuitions to advanced theory is based on either turning on a parameter that leads from classical limit to a non-classical regime, such in the case quantum mechanics, or switching to a different framework that differs from the old one away from its intuitive limit, such as in general relativity. The theory's empirical implications now can be intuitively grasped close to the classical limit where the theory meets intuition. So that's why heuristics and this intuition close to the classic that applies close to the classical limit are connected. So we find and develop advanced theories by thinking about neoclassical behavior, and then allow the free parameters that control the non-classical aspects to move towards a deeply non-classical regime. That would be the idea, how theory building or identifying, finding theories that move away from our intuitions work. So to give a specific example, how this would play out in a specific case, let's say Einstein had reasons to look for a theory other than Newtonian gravity, for conceptual reasons mostly. And when he looked at, tried to understand Newtonian gravity, tried to understand where in Newtonian gravity there would be something conspicuous that might allow him to move beyond it, he would find the equivalence principle that is not explained in that context. And this equivalence principle then, still in the old context, might be suggested, might suggest, let's say, that gravitation may be fully a property of space-time. So if there is a way of making that work, that would establish the equivalence principle. And then one would search for a space-time degree of freedom that can control this gravity on that basis. And one would notice that curvature can play that role. So that works. So it works first within the context of the traditional intuitive theory, and then conceptually, the aim is to conceptually introduce new degrees of freedom, new parameters, new elements that allow for a deeper explanation of what has been found in the old context. So that would be one way of doing that. Of course, if you look at other examples, the story would look slightly different. But the idea is that in cases like those, the reasoning only works because there is a limit close to which the GR phenomenology looks a lot like Newtonian gravity. And this closeness is controlled by a free parameter, in this case, the gravitational constant. So if one thinks that this is the heuristics, this is the process in which, based on which physicists find their new theory, then the question is, okay, so how would this work in a theory without free parameters? As we have heard, it is plausible that a final theory has no free parameters first, and in second, we know that string theory at the fundamental level does not have any free parameters. But the problem seems to be that if there are no free parameters, one cannot move away from the neoclassical at the fundamental level, which means that the normal heuristics of theory building may be suspected to break down at the step towards a final theory. So that would then create a problem for this last step due to the fact that a final theory may not have free parameters. Now, of course, one might ask the question, we know that string theory was found, and if this is claimed to be a final theory without free parameters, why was it found at all? And the answer is that string theory was developed perturbatively and based on, if one makes the calculation, makes explicit calculation, then based on choosing the ground state that corresponds to a small string coupling, so that the perturbation theory works nicely. So at that perturbative level, and that, of course, the intuition then would also go along with this perturbative level where one can understand string scattering. So what it means is that at the perturbative level, one does move close to a classical limit, and the normal heuristics still works. And this works, goes quite a long way of being effective, because one can infer properties of the full theory, such as its lack of free parameters, by looking at the basic properties of the moving string. But one cannot understand the full dynamics of the theory based on that perturbative approach. Now, in string theory, the most effective way of moving beyond the perturbative approach, then, of course, are dualities. And there are quite some dualities known in string theory. I want to focus on T and S duality here. And the idea, as already described, is that dualities establish the empirical equivalence of specific states of two different theories. In the end of empirical equivalence of two different theories. And those states are linked to each other under inversion of parameter values, or the exchange of some parameters. And on that basis, string dualities have established that there is a web of, there are several different classical limits of one and the same theory. So the way this worked was that first those theories had been identified separately as separate theories, and based on dualities, it was understood that they are classical limits of one and the same theory. So what happened was that string dualities established that theories with entirely different classical limits are empirically equivalent. And what one can do is one can start with the theory A in a neoclassical limit, and duality will move will identify this with a theory B in a highly non-classical, non-perturbative regime. Then, however, I can change the parameter value that characterizes, that controls the leads towards the classical limit of that theory, and move it close to the classical limit, and I end up with the same theory close to the classical limit, which then is a different classical limit of the theory. So that is the way this works. And if one looks at this in the case of S and T dualities, we have here this pattern of dualities. And what I have added here, just to make this point, is that I distinguish between the deep quantum and the neoclassical regime in each case. And so here I have T dualities and S, this is an S self duality, T and S dualities. And then I have the correspondence between a string theory in 10 dimensions and M theory, where the 11 dimension, where the 11th dimension that corresponds to the dilaton field in the string theory. So in this case, there is not that much of shifting from classical to non-classical, but still there is a kind of duality relation. So what is important here, that in all those cases, there is this parameter value, so to say, the green arrow, that can bring this theory from a deep quantum towards a neoclassical regime. So what it means is that these dualities have been established based on the presence of those parameters that can be related to each other from the original theory to the dual theory. Therefore, one can say that those dualities leading to the deep non-perturbative regime, but they don't lead away from the level of discussing ground states. So they are an effective way of getting a better understanding of the theory, but they may, for that very reason, not be sufficient for finding a calculable fundamental formulation, because they are based on specifying those theories that have those neoclassical limits. And these neoclassical limits, those theories that have the neoclassical limits, allow for calculation close to that classical limit based on a perturbation theory, but they don't allow for calculation of the full theory. So what happens is that those dualities somehow allow to encircle the full theory. And the problem, of course, of string theory today is to reach beyond that. And it's so difficult to do that. Now, if one views this problem from this perspective of lack of free parameters, the point may be, or the problem may be related to the fact that there are no free parameters in that theory. And a fundamental theory without free parameters may be best, or may have a best formulation that does not rely on parameters which individually lead to a classical limit. So if something of that kind is the case, then it is excessively difficult to find this formulation of the theory, because the normal heuristics that leads towards theory building, or that leads towards acquiring a certain perspective, a certain understanding of a theory, does not work in this case. So one might then imagine two kinds of theories: those with a manifest classical limit, which allow for calculation of neoclassical processes, and those without a manifest classical limit that allow only for calculations that would allow for the calculation of the fundamental dynamics. However, there is a heuristic, as we know, finding theories or representations of theories of type A, but there is none, at least at this point, for finding theories of type B. And if that were the case, that would mean that there is a connection between lack of free parameters and these long-term problems to find the full theories of quantum gravity. And since lack of free parameters may be viewed as an indicator of finality, there would be a connection between finality and chronical incompleteness. So of course, this doesn't mean that such strategies to find theories of the second kind will never be developed. They may be developed, and clearly that may be a task for physics to do so. But it's a task of a different category, let's say. Now, of course, it's not clear whether a calculable universal theory exists at all. It might be that such a theory is out there, more or less inaccessible or very difficult to access. It might also be that final universal theory does not, calculable universal theory does not exist in the sense one is accustomed to it, in which case then final theory category might still apply, but it would be an even more limited affair than what has been suggested up to this point. So then one might even more reduce the characteristic of a final theory, and it may not play any reductionist role as the fundamental theory from which all the applied models can be extracted or deduced, but in that case, the final theory might merely amount to a general conceptual framework based on which specific models can be built. If such a scenario might apply, one might still talk about finality. One might still have a conceptual framework in that case that represents a characterization of fundamental physics beyond which no improvement, conceptual fundamental improvement can be made, but that does not amount to a fully spelled out Chronical level theory. So of course, much of in particular those last slides was hugely speculative and just thinking about options one might think about. But the upshot, I would suggest, is that it may be profitable to think about finality in a broader sense, in a sense that allows all these speculative scenarios that I've briefly mentioned here to be covered by it. And it would still be constructive to think about finality in this way, because it would be a way of understanding the difference between previous stages of theory building and the status of theory building physics finds itself now. And that's where I want to conclude. Thank you.
So first in line, we have Joanna. Please go ahead, Joanna.
Thank you. I have a clarificatory question about this issue of ground states. So in classical theories, the evolution of the universe is determined by giving the laws or the dynamical equations and initial or boundary conditions. And my question is whether this choice of ground state is as analogous or similar to the choice of initial or boundary conditions in classical theories.
It's something slightly different. So it is in a quantum field theory, you have this situation where you couple fields to each other. You write the Lagrangian of this entire system, and then you look for states of minimized energy, local minimized energy. And it turns out that these so there may be a fairly complex relief of energy values that specifies a lot of such local minima, and that's the spectrum of ground states of the theory. And you also find that in a string theory context, and it turns out that in a string theory context, due to this highly complex situation in string theory, where you have you have 10 dimensions and you have lots of different oscillation modes, lots of different objects that can be in that high dimensional space. And the effect is that there is a huge number of possible local minima, and that's what is called the landscape in string theory.
Okay, thank you. Can I ask something?
Yes, go ahead.
Yeah. So my question was motivated by your claim that the assumptions we already have in string theory determine all the further details, including that they resolve the problems you mentioned in the beginning. And and in classical theories, one often thinks about the choice of initial conditions as something that is not determined by a theory, as something that is, in metaphysical terms, accidental, in contrast to laws of nature. So my question behind that clarificatory question was whether one can think about the choice between different ground states in a similar way as a kind of accidental choice that just happens, and we can't explain why this one or not the other is realized in a similar way in which one often thinks about the choice of initial conditions.
So in the understanding would be that choosing one ground state in string theory would be a dynamical process. It is a quantum process. It is not it's not external to the theory. So it is something different from a situation where you have the theory and then you set something to a certain value, but rather you have this fundamental theory that characterizes the fundamental dynamics of the world described. And then you have those energetically favored constellations that will be that the system will probably enter. And if you have many ground states, it's not deterministically clear. It's not a deterministic process that leads to one of those ground states, but there would be probabilities for selecting each of them. That would be the idea. So this is a quantum process, and it is a probabilistic process. But the problem is that one doesn't know the fundamental laws that guide that dynamics.
Thank you very much.
Thank you. Aaron is the next. Please go ahead.
I must first apologize because I probably don't know enough of the physics and mathematics to ask this question in the best possible way. But it's a question about biology, and in particular about the processes of control and the uses of information in control and how they develop and become increasingly complex and intricate and interrelated during the development of an organism. For example, I apologize to people who've heard me say this before. If you think about an egg, it starts off with a very small controlling portion with DNA, and then relatively amorphous additional stuff there. And it's all enclosed in a shell. And although some energy may come in through the shell, there might be some exchange of gases. Mostly what happens is under the control of the particles inside the egg, initially all controlled in a very small space by processes involving DNA and so on. But gradually, as the organism that is being constructed becomes more and more complex, it becomes more and more highly differentiated. For instance, if it's a chicken or a turtle or an alligator or whatever, it becomes more and more highly differentiated into different kinds of stuff which have been assembled under the control of all these processes, nerve fibers, blood vessels, bones, tendons, muscles, all sorts of additional things. And these also have to be arranged in ways that support biological functions. Some of those functions start being supported inside the egg. Others for instance, consuming food and digesting it will not happen until after the thing comes out, but nevertheless, they have to come out. And even control functions, for instance, there are animals that come out of an egg and they know what to do to get food. They can walk to water, they can paddle around, they can peck for food. They don't have to learn. So all that information has got to somehow be assembled during those processes in there. And I'm just wondering whether the theories that you're talking about would allow for structures and processes at a different level, not defined in terms of the normal numerical properties that physicists measure, but in terms of functional relations, types of information, notions of control, and so on. Would that be something that could be an extension of string theory without contradicting the claim that it can't be extended, that it's complete?
Well, the statement that string theory can't be extended is a statement about fundamental levels of physical theorizing. Of course, this does not mean that higher levels of conceptualization that characterize, for example, biological processes are in any way at variance with string theory. So string theory would be entirely neutral with respect to those conceptualizations if you compare it to any other theory of fundamental physics. So there is no implication in that direction whatsoever. What I might mention in this context, just talking about, not about the conceptualization of complexity in biology, but the fact that complexity arises in biology. In that respect, there is a possible implication of string theory, and that's the multiverse conception that has been developed in the context of string theory and inflation, and that provides an entropic argument for fundamental physical conditions that allow for development of complex structures. So in that sense, there is a connection. The connection is that it may be, in some sense, let's say, surprising that the world is of a kind, of a type that allows for complexity of the kind we observe in biology, for example. And the complexity of the string landscape, the fact that the string landscape is so huge, based on an entropic argument, can offer an explanation for that. The entropic explanation would then be that actually it is highly improbable that a system, a string vacuum, let's say, allows for that type of biological complexity. But given that the multiverse is so huge, meaning that basically all of those ground states of string theory are realized somewhere, there will be patches in the multiverse where such complexity can develop. And then the entropic argument would say, on that basis, obviously those parts of the multiverse where complexity does develop are those that have the right characteristics. So in that sense, there is a connection actually between the fundamental level and the fact that complexity, this high level of complexity, can be observed in our world.
Just a last small point about that. One of the facts about these developments is the minute amounts of energy involved compared with normal human design manufacturing processes, which produce things much less complex than a newly hatched chick, but they require far more matter, far more energy, far more space, and typically longer times. And I'm just wondering if there are any ways in which there's something special about the string theory that sheds light on that. But perhaps you've said enough about that already.
Yeah, I don't think that with regard to that specific question that string theory can be of any help.
Thank you very much. Next in line we have Karen.
Oh, hi.
Hi.
I'm just curious if the proposal kind of gives any heuristic value, like, does it tell you a bit of kind of how the theory could be developed or where we could look to find the full formulation? Perhaps in certain ways it could connect up with the perturbative formalism, because that's how you have the connection with known physics, something like this.
Yes, it's a good question. It's a question
Can it be useful?
I try to think about that question for some time. And I'm not entirely sure how far one can drive this. I mean, these are of course very general considerations, and my feeling is that just I don't think that on its own these finality considerations are sufficiently strong to serve as a guideline for theorizing or anything of that kind. I think the role they, if in best case, let's say, they might they might offer a different way of thinking about this fundamental problem. So the problem that fundamental physics seems to be stuck in this way, and maybe that rather than suggesting specific directions of theorizing that I would think clearly need to emerge from more specific physical considerations, it could contribute to some kind of awareness of the situation the physicists finds themselves in. That would, in my understanding, be the role this can play. I don't think any more than that is realistic. Yeah.
Thank you. Vincenzo.
Oh, many thanks. Thank you very much for the wonderful talk. I understood that you said that string theory is final in a new way, new weaker way. That is, it is new revolution, conceptual revolution are possible, but there is something that is final in the sense that it is without free parameters, in the sense that it establishes what is the smallest thing in the universe, and from this point of view, it is not possible to have a different final theory. So there is something that is definitive, even if it is something that is very weak. But I think to what happened in 20th century physics, that is on one side quantum mechanics, on the other side general relativity. And quantum mechanics clearly was a revolution based on the fact that we found that going in the bottom, going at a smaller level, we found something completely different, not completely, strongly different from what we knew about our normal everyday level. But general relativity is a quite different revolution in the sense that the concept of classical physics has been, in a certain sense, exchanged. The relation between matter and space and time was strongly changed in this concept revolution. And so it is possible that a final theory or a more final theory, if this notion has sense, could be something of this kind, in the sense that it is possible that would be an exchange of concepts. In a certain sense, I don't know if I say something correct, but it seems that different program like loop quantum gravity and causal sets aim in this direction, in the sense that one perhaps can say that string theory is a sort of extension of a field theory on the main line of the physics of the last 50 years. On the other hand, the other approaches that are quite less developed are attempts to make sort of revolutions more similar to what happened at the beginning of 20th century in general relativity. I don't know if what I said has sense, but is it a doubt? Thank you very much.
Yeah, thank you. Yes, I would agree that. So what I said was that the problem of chronicle incompleteness is shared by all approaches to quantum gravity. The final theory claim is not, of course. So that's an interesting distinction between those approaches. In the loop quantum gravity and other approaches to quantum gravity that don't aim at this stage in any case at being universal, also don't have a clear theory intrinsic argument, to the best of my understanding, that would establish their finality. The question then would be if, let's say, if such a theory pans out, and if string theory develops further, what the relation between those theories would be, what the relation between those different approaches would be, whether they would need some additional posits maybe somewhere in order to include matter in an adequate way, in order to account for gauge field theory or whatever. I don't really know, but it seems to me that it's not clear at this stage what would be needed or what could be done in order to develop those theories further. So it seems to me that those three finality claims, or the three reasons for making a finality claim in the context of string theory, are really characteristic of string theory specifically. And that's clearly a difference. Maybe if I have some time, I might also point at another interesting, what seems to me to be an interesting point, which is that before quantum mechanics and the theories of and general relativity, let's say, having a final theory, there was no genuine theory intrinsic argument in favor of finality in the context of Newtonian physics or Maxwell, but it was a plausible possibility. So one could even say that, one could assume that Newton and Maxwell in conjunction cover all physics. They are not fully unified, but maybe the final theory is not fully unified. So in that case, that was a plausible understanding. While from the point when general relativity and quantum mechanics had been established, let's say there were good arguments to think that those theories cannot be final, that one would need something like quantum gravity in the end to end up with a theory that covers all of this, and that they couldn't just be placed next to each other in the same way. So therefore, throughout the most of the 20th century, there just was no candidate for a final theory in this universal sense. And only at this stage this has reemerged, only in the context of string theory.
Thank you very much.
Thank you. Next in line we have Pedro.
Thank you. Thank you, Richard, for your talk. So for starters, I'm not aware of the state of the art of string theory right now. So let me just point out whether you know, its current status regarding background independence. Well, the reason I'm asking this is because, as you know quite well, I guess, the reason why these different approaches to quantum gravity, Gaussian spin forms, group field theory, causal sets, CDT, etc., started in the first place is precisely because string theory in that regard is a fairly traditional theory in the sense that we just play on an absolute space and time. It's conceptually speaking, it's pretty close to Newtonian mechanics in that sense. So it's true that, okay, the fundamental level, there are no free parameters, but what that means is just basically once you have a fixed space-time, say ADS, in this well-famous ADS-CFT conjecture for start, for example, but once you fix that space, that's all there is. So, so as a caveat, as I start and say, I don't know what the status on background independent is right now. Why I think this is relevant for this finality business is that for me, I pretty much sympathize with the other camp. So in terms of fully non-perturbative and background independence theories to physics in general and to quantum gravity in particular. So it's hard to see to me that a theory that enjoys absolute structures could be qualified as final at all, because empirically speaking, it's fairly easy to say that basically just by some sort of symmetries, you can describe precisely the same predictions and making and matching empirical data with less structure, and so making in this case space and time being relational. I don't want to go as far as say that basically they are going to disappear, because this is a subtle point, but at least just relational. So just to see, and depending on your answer, I would step in again. Thank you.
Yeah, background dependence. I mean, a lot of discussion has happened on this background independence, and of course, it was the background independence advantage was stressed by loop quantum gravity and other approaches. Background dependence in string theory is a characteristic of the perturbative approach. So what it says is that when you characterize scattering of individual strings, you do that on a background. It does not mean that the full theory of string theory is background dependent. It wouldn't even be clear what that should mean, given that gravitons are string oscillations. So there is no other part to the other story to curvature, to space-time curvature in string theory than the dynamics, right? So the full theory clearly is background independent in any sense. The problem is that one doesn't have that full theory. So if one talks about string theory as a final theory, not as the methods, the perturbative and duality-based methods that allow us to say something at the theory at this point, but by saying this, we mean the theory that is characterized based on applying those methods, then that theory is not background dependent. There is no sense in which background dependence even would be a meaningful characterization of this. So the problem is that the level of theorizing at which this background independence gets fully established, let's say, at which the full dynamics of the theory plays out, that this level of understanding has not been reached. But it's not an issue for the theory itself. And if one talks about theory, string theory as a final theory, the sense in which one talks about is this projection, what the full theory that we mean, that string theorists aim at when they develop their methods of understanding the theory, whether that theory is final. And that's not a background dependent theory.
All right. So, okay. Yeah. Okay. Thank you for the update, because, well, back in the day, I was in this research field, and that's basically was one of the reasons why I got a bit disappointed. But okay, yeah. So I see the situation. Thank you.
Thank you, Pedro. I have a question. And in one of the slides, you said that in order to justify the fact that string theory being chronically incomplete and final is not that big of a deal, you said something like, we have the fundamental posits of the theory. We know how the world is according to the theory. What we don't know is the full dynamical structure of the theory. So I was wondering whether this has some major impact on the metaphysics of laws of nature, because long story short, the most well-established metaphysics of laws claim that from how things are, we can infer the laws, the fundamental laws of the world. Now, it seems to me that from what you said, it follows that even if we know how things are fundamentally according to string theory, still from this, we cannot infer the full dynamical law. So this seems to me a reason to say dramatically change our views on the metaphysics of laws of nature. So I would like to know your take on this.
Yeah, maybe I can make two comments on this. First, I wouldn't say that the fundamental posits of string theory have been identified. What I mean is that a sufficient set of posits has been identified that clearly, unequivocally identifies the theory. So that was meant by that. So we don't need any further posits to add to what is there already in order to specify the fundamental theory. That would be the idea. Whether those are, and interestingly, initially those posits came from a very perturbative end of the story, right? Thinking about an oscillating string, about the boundary conditions you can put on that string, how many ways of doing this you have, and then you end up with the string theories. That would be the starting point. that is a starting point that is entrenched in this perturbative way of thinking about the theory. But the suggestion is that nevertheless it is sufficient for fully specifying the theory. So it's a clear laid out goal to understand what the full theory that fits into this picture, that fits those posits would be. That's the idea. In this sense, it is a sufficient set of posits. The question of fundamentality indeed is also rendered fairly difficult in string physics because of those duality relations. So most of the characterizations of an ontological realist would try to find in a fundamental theory are not, let's say, are not duality transformation invariant, right? So you go to a different theory, and different objects are fundamental ones. Different objects are, you have different types of objects. You have different dimensionality of objects, all different symmetry structures, all whatever you would want to aim at. You would find is not uniquely determined, but you can have different perspectives, different formulations of the theory that start from different, let's say, fundamental posits in this sense. And of course, this gets even worse if you look at gauge gravity dualities at ADS-CFT, where one of the dual theories is not even a string theory at all. It's a conformal field theory in the case of ADS-CFT. So if you ask the question, okay, so what are the fundamental building blocks according to this theory? The answer would be there are no fundamental building blocks in this sense. So if one would try to adapt a kind of scientific realism to this, structural realism would be the most plausible attempt. I would think. So it is the uniqueness of the theory and the rigidity of the theory lives at the level of conceptual constraints rather than at the level of fundamental building blocks.
Thank you. Let me follow up on that, because you said something very, very interesting. The fact that the most suitable metaphysical take on the string theory formalism is structural realism. And I guess it's some sort of radical form you have in mind, where basically what exists is just structure. That there are fundamentally not real relata that implement this structure. But I can also suggest another scientific realist take on the theory, which is a perspectival one, because as you said, each particular model can be considered as a certain scientific perspective. And then basically we can embrace the whole framework, including all the dualities, in a conceptually neat way, if you want. So I don't know what you think about this perspectival take on string theory, and whether actually perspectivalists can use your work on this subject to justify their position.
Yes, I mean, personally, I don't think I would agree that perspectivalism is that there is some striking parallels, let's say, between these perspectivalist between a perspectivalist point of view and this situation with respect to string dualities. to me, nevertheless, I prefer a different perspective on that. Because to me, what seems to be going on here is that the ontological perspective on fundamental objects is a perspective bound to the classical limits of the theory. So my conclusion from what I see in string theory would be that it awards a secondary role or a different role to ontology. Ontology is not a fundamental characterization of the world or of a theory. It is a characterization of a classical limit. And the farther we move away from that classical limit, the less it makes sense to talk in terms of that ontology. It is an increasingly inadequate way of characterizing the situation away from those limits. And it also does not have much sense then to shift to another ontology of that kind, because you may end up in, I mean, if you think about the situation, for example, in terms of this web of dualities, you may up in a situation where none of those different string theories would be in a neoclassical state. So you're just profoundly, from any perspective you may choose, you are far away from a classical situation, which then would mean that none of those simple, straightforward string ontologies is actually a very good characterization of what's going on. There is no, the entire perturbative view is not awfully helpful then in those regimes. So yes, so that would be the most plausible view on this, I think.